Welcome to Chapter 6 of the NFV 101 course. This chapter talks about the involvement of CableLabs in the area of NFV and how it particularly addresses the concerns and requirements of the cable industry. CableLabs involvement with NFV is at three layers. The first layer is industry leadership, is to make sure that some of the leading standards bodies and open source projects are aligned to the requirements of cable operators. The open source projects and standards bodies that CableLabs is involved with are specifically ETSI. We've talked about ETSI in great detail, and we've looked at many of the ways CableLabs is engaging with ETSI, but we will look at some more specific details. The four projects that CableLabs is perhaps most involved in is OPNFV, Open Daylight, OpenStack, and Open Source Manual. And we've talked about all four of these projects in prior chapters. Now this list is not comprehensive. There are many other open source projects that CableLabs is involved with. For example, one of the main ones that comes to mind is Kubernetes. But in interest of keeping the slide manageable, we have listed four. The next area of engagement is an SDN NFV application platform stack, which is called SNAPS. And we are going to spend a good part of this chapter on SNAPS. So we'll hold off on a further discussion until subsequent slides. And then the third area of involvement is interop testing and demos for cable-centric NFV application. The key here is the demos that are developed and the testing that is conducted is specifically for cable-centric applications. So now let's look at the first one, industry leadership, specifically with respect to ETSI. So let's talk about SNAP. So SNAP is a CableLabs initiative to optimize the NFVI and VIM layers for NFV and SDN. So that's really the idea. Now you might say, why do we need to optimize? I mean, there are upstream projects focusing on NFVI and VIM. Why don't you just use them as is? Well, there are many reasons. Over and above just the availability of the project, there are things like installation. So the software has to be installed with the right components, specifically for the NFV use case. So the right projects, the right software components have to be installed. So you could call this the reference architecture stack. So that's the first challenge. The second, and in this reference architecture stack, it's not just the compute technology, but you have to weave in the right networking technologies to address NFV and SDN, the right storage technologies. In addition to installation, you have to worry about management and monitoring. So these are all things that are taken care of by the SNAPS program, as we will see in a little bit. It's aimed at developers. It's open source. The code is open, the APIs are open, and it's completely vendor neutral. It runs on commodity servers, sort of an obvious point for NFV. It integrates the latest code, so it's constantly moving along with upstream projects in concert. And it's optimized on performance and latency for both sort of core NFV SDN applications and edge computing. So that's really the introduction to the SNAPS program. Now let's look at it in more detail. The SNAPS Platforms project has 5 projects envisioned. 1 is future and 4 are active. So what it shows is at the bottom there you have access networks. You have the remote PHY concept that we discussed in the last chapter. Very similar concept is remote MAC and PHY. There are Wi-Fi access technologies, LTE, and 5G. So that's the bottom layer that's shown on the slide. Above that, you have the head-end hardware. So you have servers, you have rack switches, you have access switches, core switches, clocking. Next, you get into the software layers. So SNAPS is all software. The first layer is bare metal operating system, SNAPS boot. Before any software can be installed on a server, the basic operating system setup has to be done. So the node has to be provisioned. And then you can deploy higher level software on it. So SNAPS boot deals with this specific problem of installing the operating system on a bare metal system. Above that are SNAPS-OpenStack and SNAP-Kubernetes. We'll look at both of those. And then SNAPS serverless is a future activity which deals with serverless computing, which in some sense is a misnomer. Of course, there's a server, but the idea is that the application author or the person who writes the code doesn't have to worry about a server. They don't have to worry about where the code is deployed or how the code is deployed. Hence the term serverless. And then the application layer is SNAPS-OO. This is a project that's under the auspices of OPNFV and SNAPS automation. In the next few slides, we are going to look at SNAPS Kubernetes, SNAPS-OpenStack, SNAPS boot, and SNAPS-OO. With reference to the HC-NFV reference architecture, this is where all the SNAPS projects fit in. Now we are going to look at each of them in more detail, so don't worry if you don't fully understand what each one does, but this just is an attempt to show where the different SNAPS projects fit. The SNAPS boot project, which is operating system provisioning, fits in with the NFVI, specifically compute, virtual compute. SNAPS-OpenStack and SNAP-Kubernetes fit in the virtualized infrastructure manager category, and SNAPS-OO can be considered an API layer on top of OpenStack, and in that sense, a VNF manager. One area where SNAPS pays particular attention is Dataplane acceleration. As we saw in Chapter 2, performance is a very important requirement for NFV, and addressing it correctly can directly impact the financial business case for an NFV service. Dataplane acceleration can be done at 3 levels. It can be done using purpose-built hardware. It can be done using hardware assist, so software but with hardware assist. And then finally, purely software or some architectural approach. Let's look at all 3 categories. Purpose-built hardware includes items such as smart NICs that might have OVS offload, VXLAN offload, P4 interfaces, etc. Can be FPGAs, can be graphical processor units, GPUs, that are used for high-performance computing, artificial intelligence, machine learning type applications, and custom ASICs, for example, crypto, which can be very useful for security. The next one is hardware assist, which includes items such as memory or CPU pinning, huge pages, cache-related features, SRIOV. And then the last bucket is software or architectural-based approaches to dataplane acceleration, such as DPDK, which is a user mode technology that uses polling instead of interrupts to dramatically speed up packet processing. FIDO, it's an alternative to OVS that we touched upon in an earlier chapter that uses parallel processing, packet processing to speed up performance. IOVisor, it's a kernel-based technology to programmatically speed up data plane acceleration. Open Data Plane, it's an abstraction layer that allows for proprietary data acceleration hardware, but standards-based APIs. And then real-time Linux. So all of these are data plane acceleration techniques. You can look at HC-NFV-per 001 document that's listed below. Now, not all of these are supported by SNAPS, but this is a focus area for SNAPS, and for the time being, SNAPS is focusing on the middle section. So all the hardware assist features that you see, many of those are included in SNAPS, and then on the software/architecture bucket, items such as DPDK, etc., are also within the scope of SNAPS. So let's start with SNAPS boot. So like we discussed in the previous slide, a server is of no use unless there's an operating system installed on that server. And this is somewhat of a tricky operation and can get complicated, manual, error-prone, buggy if not done properly. SNAPS boot attempts to solve this problem. The way it works is SNAPS boot has to be installed on a jump server or build server. Once it's installed, it can automatically provision the operating system on additional nodes, and these additional nodes could be compute, storage, or controller bare metal nodes. It's a single command with a variety of config options. You do need a certain number of networks that are connected to each of these nodes, management, tenant, and external. And it installs Ubuntu 16.04. So that's SNAPS boot. Next, we'll look at the NFVI and Vim layer. And the two projects here are SNAPS-Kubernetes and SNAPS-OpenStack. SNAPS-Kubernetes deals with the Kubernetes container orchestration engine. We talked about Kubernetes in a previous chapter in some depth, that when you have an order of magnitude more instances with containers, because they're such light footprint, they're more ephemeral than virtual machines, you really need a very sophisticated management engine, an orchestration and management engine, and that's exactly what Kubernetes is. It can take an application that's described, that's further broken down into pods, and each pod then consists of containers. And that whole application is orchestrated, and the lifecycle management is done by Kubernetes. So you might ask, well, Kubernetes exists, so what's the use of additional layer like SNAPS-Kubernetes? So like we discussed a couple of slides ago, you have to install Kubernetes, and you have to install the right version of Kubernetes in an automated manner. The right hardware acceleration features have to be chosen and configured. The networking technologies have to be, again, selected for NFV SDN and installed, and same thing with storage, meaning the reference architecture stack that's deployed has to be well suited for the SDN NFV use case, which is exactly what SNAPS-Kubernetes is. In addition to the functionality that we just discussed, there's also management, authentication, monitoring, and these are also aspects covered to various degrees by SNAPS-Kubernetes. So if you go down the list, container orchestration and resource management, tooling for monitoring and diagnostics, microservices architecture for application development, easy management of container networking. So this is an important topic. The networking paradigm of Kubernetes is really geared towards web, enterprise-centric applications. It really is not that well suited out of the box for NFV and SDN. And that's really a gap that's filled by SNAPS-Kubernetes by allowing access to a variety of SDN technologies such as Weave, Flannel, and Calico, but then also offering advanced features like MAC VLAN, DHCP, SRIOV, and perhaps another very interesting one is multi-homed pods, where a pod can have multiple IP addresses. Pre-provisioned, pre-configured and provisioned security components, DevOps enabled. In addition to what we just mentioned, there's also support for Ceph-based persistent storage, boot volumes for pods. There's a Kubernetes dashboard pod. The pod shows health notifications and visualizations of the networking topology. All the NFV-centric hardware acceleration features that you might expect are supported, like CPU pinning, huge page support, pod node affinity, anti-affinity, and availability zones. And finally, there's other infrastructure support like authentication, role-based access control, support for logging and diagnostics, additional monitoring for CPU, memory, and network usage. So that's SNAPS-Kubernetes in a nutshell. At this point, the number of container-based VNFs are limited, but we expect them to grow over time. And the benefits that we looked at in the previous chapter in terms of VCCAP core and RPD, some of the numbers were quite stunning. Those numbers are expected only to become even better with SNAPS-Kubernetes, where a container footprint is lighter than a virtual machine and the boot time is faster. Next is SNAP-OpenStack. SNAP-OpenStack provides a variety of benefits very similar to SNAPS-Kubernetes. So it's an open source OpenStack installer based on OpenStack Cola. It supports the OpenStack Queens release. Now OpenStack Cola, what it does is it containerizes OpenStack, and it deploys the containerized version of OpenStack, which makes OpenStack as an application a lot lighter, a lot easier to manage its lifecycle, a lot easier to upgrade, etc. So from that standpoint, it's a very modern, sophisticated way to install OpenStack. So again, like we talked about Kubernetes, the reference architecture has to be tuned to the SDN and NFV use case. So it's a rich installer with features. We talked about containerized OpenStack net support, but provider network flexibility, etc. It installs OpenStack on a set of nodes provisioned by SNAPS boot. And the major projects that are supported currently are Nova, Neutron, Glance, Keystone, Horizon, Heat, Open vSwitch with DPDK. But these are not the only projects that are relevant to an NFV SDN use case. There are many others. And those are installed by SNAPS-OpenStack as well. For instance, Stacker, which is a VNF manager, Mistral for workflow management, Magnum for container support, Barbican for key management security, Ceilometer for metering, Noki, Redis for database, Cinder for storage, and Steph for storage as well. So these are all additional OpenStack services that are deployed by SNAPS-OpenStack. SNAPS-OO is an object-oriented API layer written on top of OpenStack APIs. So in that sense, it's a middleware project. It's an official OPNFV project. It's a lightweight orchestrator, and it overcomes a number of limitations with the OpenStack API. So the OpenStack API may be great for a variety of applications, but for things such as testing, it's cumbersome. So if you want to deploy a set of OpenStack resources and clean up the environment completely when the test is done, the current API has a number of limitations, and those limitations are solved by SNAPS-OO. In addition to solving the API issue, there's an additional bonus. SNAPS-OO comes with about 400 tests for OpenStack, Vim, and NFVI-based tests. As a testament to how successful SNAPS-OO has been, in just 15 months, 4 other OPNFV projects have embraced SNAPS-OO. And those projects are FunkTest, which deals with functional testing of NFVI and Vim, Yardstick, which deals with performance testing, StorePerf, which is another performance testing project specifically testing storage performance and connectivity from compute to storage, and SFC, which is service function chaining. So these 4 projects have switched over to using SNAPS-OO instead of calling the OpenStack API directly to really streamline their code and make it a lot more predictable and cleaner. We encourage everyone to try out SNAPS. SNAPS is fully open source with open APIs. So you see the 3 URLs for SNAPS boot, SNAPS-Kubernetes, and SNAPS-OpenStack. SNAPS-OO Because it's an official OPNFV project, it's under that umbrella. The code is available through the OPNFV website as opposed to CableLabs GitHub. But all of this is available, so please try it out and see how it works for you. Now let's go to the third aspect of CableLabs engagement with SDN and NFV. The first two being industry leadership with standards and open source projects. Second being the SNAPS initiative. Third one deals with interop and demos. This is managed through the Kyrio subsidiary of CableLabs. And Kyrio, just as a quick overview for those not familiar, for manufacturers and service provider, Kyrio accelerates and deploys new network innovations into the ecosystem. So they have activities ranging from proof of concept systems integration, infrastructure validation, hardware and software, VNF evaluation, conformance, performance, and interop testing, and then custom testing. A lot of these services are fee-based. It is a for-profit subsidiary of CableLabs. And you see SNAPS in the middle. So all of these activities are adjacent and complementary to SNAPS. Let's look at a concrete example. So this is an example of a vendor-neutral SDN NFV lab integration example. It was done as a demo. So what you see is on the right-hand side, you see a mobile device that is connecting to a cable modem through a variety of access technologies, CBRS or small cell LTE, and Wi-Fi. And these access technologies come from CASA systems. They then feed into Intel Puma cable modem through a coax connection that goes to a remote PHY device, which then converts it into Ethernet over fiber. That feeds to an Intel white box server, which is running SDN NFV services. The bottom layer is SNAPS boot to provision bare metal servers and to provision the operating system. On top is SNAPS-OpenStack, providing the NFVI and Vim layer. And then you have, as I mentioned, the CASA access technologies come with corresponding VNFs. And you get access VNFs, VEPC, and VCCAP core, all from CASA. And this was integrated, these technologies were integrated in the Kyrio lab. And they provided the end-to-end environment for the collaboration between three entities, Intel, CableLabs, and CASA. And the end demo showed a cell phone being able to roam between Wi-Fi, LTE, back to Wi-Fi. And the cable technology was DOCSIS 3.1. So this is just one example. There are other examples of such integration as well. In conclusion, we saw how CableLabs is providing leadership in NFV in the areas of open standards, open source software, and interop, with a special focus on cable-related use cases and concerns.